A transistor consists of a single crystal of germanium or silicon, which is grown in such a way that it has three regions. Transistors can be divided into two types: PNP transistors and NPN transistors. In NPN-type transistors, the central region is P-type, which is sandwiched between two N-type regions. In PNP-type transistors, the N-type central region is sandwiched between two P-type regions. The central region is known as base, and the other two regions are called emitter and collector. Usually the base is very thin, of the order of 10 micrometer. The collector is comparatively larger than the emitter. The emitter has greater concentration of impurity as compared to the collector. A transistor is a combination of two back-to-back PN junctions, emitter-base junction and collector-base junction. For normal operation of the transistor, in a circuit, batteries VBB and VCC are connected in such a way that its emitter-base junction is forward biased, and its collector-base junction is reverse biased. VCC is of much higher value than VBB. The figure A1 shows the biasing arrangement for NPN transistor, when the transistor has been represented by its symbolic form. Figure A2 shows the same for a PNP transistor. It may be noted that polarities of the biasing batteries, VBB and VCC, are opposite in the two types of the transistors. In actual practice, it is the NPN transistor that generally used. So we will discuss NPN transistors only. Figure B1 shows an NPN transistor at the instant when biasing voltage is applied. Electrons in the emitter, shown by black dots, have not yet entered the base region. After application of the biasing voltage, emitter-base junction is forward biased, so emitter injects a large number of electrons in base region. It is shown in figure B2. These free electrons in the base can flow in either of two directions. They can either flow out of the base, to the positive terminal of VBB, or they can be attracted towards the collector, because of battery VCC. Since the base is extremely thin, very few electrons manage to recombine holes, and escape out of the base. Almost all of the free electrons injected from the emitter into the base are attracted by the collector, due to its large positive potential VCC. It is shown in figure B3. In a normally biased transistor, due to already mentioned flow of electrons, we can say that an electronic current, i.e. flows from the emitter into the base. A very small part of it, current IB, flows out of the base. The rest of it, IC, flows out of the collector, as shown in figure B4. The flow of conventional current is shown in figure B5. According to Kirchhoff's current law, it can be seen from the figure that IE equals IC plus IB. As very few electrons flow out of base, so IB is very small as compared to IC. It is also found that for a given transistor the ratio of collector current IC to base current IB is nearly constant. That is, this ratio is called current gain. Its value is quite large, of the order of hundreds. The equations 1 and 2 are fundamental equations of all transistors.